Hello friends, welcome to this video lectures of experimental stress analysis. So today we'll discuss about the chapter number 8, computation of stresses, part 2. So before moving to this part 2, so in the same chapter, that is in the part number 1, we have discussed about the basic introduction of the strain rosette or the strain gauge rosettes. Then we have discussed about their basic classification, how the strain gauge rosettes are classified according to the number of strain gauges and according to the number of angles. Then we have discussed about some of the important formulas which are required to solve the numericals based on the all the types of rosettes. So in this part second, today we'll discuss about uh, the basic applications of the strain rosette. So before moving to the numericals based on the strain gauge rosettes, initially once again I will explain what is the basic application of the strain rosettes, where such types of the strain rosettes are used. Then you can understood very easily what is the basic difference between the strain gauges and the strain rosettes. So whatever the figure is there in front of you, so whatever the machine is given, so this particular machine is called as a dynamic machine. So if any component it is in rotating condition, so during that rotating condition, if I have to calculate the strain induced in that particular component, then these particular machines are used. Or if you take the example of the helicopter blades, so if the helicopter blades are start rotating, some amount of strain is also induced in the number of directions. So if I have to calculate the strain induced in that particular rotating blades, so in that case what I have to do, I have to paste the number of strain gauges at the number of location. So same the experimental setup is also available with us, that is this particular machine is called as a dynamic machines. So in the dynamic machines, so this particular central portion is called as a hub on which we can attach the blade like this in cantilever position. That means this is a rotating hub which is rotating for the different rpms. At this particular point, this composite blades are attached and the another end is free. If these blades are start rotating, the amount of strain is induced at the three locations. So here my requirement is that I have to calculate the strain induced at the three location. That means the strain induced near to the fixed end, the strain induced at the center point, and the strain induced at the free end. But when this blade is start rotating, I don't know the state of strain and the direction. Means if this particular blade is start rotating, I don't know in which direction strain is induced. If I will know the strain induced in x direction, then I can paste the strain gauges in x direction. If I will know the strain induced in y direction as well as z direction, then I can paste the strain gauge in y direction and z direction. But here, as the blades are start rotating, I don't know the state of strain and its direction. Therefore, it is required to provide the strain rosettes at the three different locations, because as in the part number 1 I have explained, if the state of strain and their direction is not known, then instead of using the strain gauges, I have to use the strain rosettes, due to which the number of strain gauges are pasted in the number of directions, and according to that I can find simultaneously the strain induced in the number of directions. So for that purpose, in this particular blade, whatever the number of rosettes are connected, so that number of rosettes are pasted, which is represented by the second figure. So if you go through this particular figure, this figure is again having the same construction like this particular dynamic machine. That is, one blade is there which is fixed at one end and the another end is free. As my requirement is that I have to calculate the strain induced in number of directions as well as number of locations. So I have to calculate the strain near the fixed end, I have to calculate the strain at the center of blade, I have to calculate the strain at the free end. Sometimes I have to calculate the strain induced near the fixed end but at the bottom side. So here if you go through this particular figure, this particular small black rectangle represents the strain gauge pasted at the different locations. But their detailed figure is represented here. So this particular figure represents at this particular point the three strain gauges are pasted. That is one strain gauge in horizontal direction, another strain gauge in vertical direction, and last, that is third strain gauge, is in inclined direction. That means simultaneously I can calculate the strain induced in x direction, y direction, and the z direction. That means whatever the this small rectangle represents, this small rectangle represents the rosette pasted at the free end. Similarly, one more rosette is pasted at the center point, then one more rosette is pasted near the fixed end at the top side, and at the last one more rosette is pasted at the bottom side near to the fixed end. So whatever the number of strain gauges are used in this particular rosette, so this number of strain gauges are the three. This is the one, this is two, and this is three. Therefore this rosette is called as a three element rosette type of strain gauge, or we can say the three element rectangular strain gauges. So like that, the number of rosettes are pasted at the different locations as per our requirements, and after that, whatever the number of three strain gauges are pasted, all the three strain gauges are having the different terminals, and this all the three strain gauges or this particular rosette is connected to this particular device. So this device is called as a telemetry strain data acquisition system. So this particular wire represents as the number of rosettes we have pasted at the number of locations. So this all the rosettes or all the strain gauges are connected to this particular telemetry strain data acquisition system. So whatever the amount of strain is induced at this particular three locations or the four locations, that all the strain values are captured from this particular rotating blade, and this is transferred to this particular telemetry strain data acquisition system. And from this particular system, whatever the strain is induced at the number of locations, that strain is transferred to your computer system through a Wi-Fi device. So this device is a non-contacting type of device. So whatever the amount of strain is induced, this strain data acquisition system will collect the data from this particular blades, and it will transfer all the strain values to your computer system through a wireless device or through a Wi-Fi system. So this is the basic construction and the basic application of the strain gauge rosettes where it is used. So from this particular figure we can easily understood that wherever the dynamic applications are there, that means if any component it is in rotating condition, as well as in that rotating condition, if I don't know in which direction the strain values are induced, in that case instead of using the strain gauges I have to use the number of rosettes at the number of locations, and by using that particular rosette I can calculate the strain induced in number of directions as well as different locations. So whatever the rosette is used in this particular application, that rosette is the three element rosette type of strain gauges. So there some specifications are also given, that is whatever the rosette is used, its length is in between 3 mm or 5 mm, then whatever the resistance of that rosette is there or resistance of the strain gauge is there, it is of 350 ohm. Their gauge factor is a constant factor which we have to consider before we have to use that rosette in any application. And last one, whatever the type of strain gauges they have mentioned, that represent the foil type of strain gauges. Why they have used the foil type? Because in the foil type the maximum area is available to paste the strain gauge on the specimen, and due to which the maximum area is comes in contact with the foil type of strain gauges, and you will get the accurate reading. So this is about the basic applications of the strain gauge rosette. So now I will play one video. From that particular video you can easily understood that is how the rosettes are work and how the amount of strain is transferred to that particular device. Just see here. Now if you go through this particular figure, in that particular figure or in that particular video, we can see the blades are start rotating. So due to that rotating condition, what happen, the amount of strain is induced in number of direction. That means some amount of strain is induced in x, y and the z, and that strain is captured by using that particular rosettes, and from that particular rosette the strain is transferred to that telemetry strain data acquisition system. Here that telemetry strain data acquisition system is not located, it is located at this particular top portion, and the amount of strain induced in that particular blades, it is transferred to the telemetry system, and from that particular telemetry system the strain is transferred to your computer system through a Wi-Fi device. So like that, in the dynamic applications where the components are rotating, in such types of the dynamic application, such types of the strain rosettes or the rosette type of strain gauges are used to calculate the strain in the number of directions, because the state of strain and its direction is unknown in such types of applications. So this is the basic applications of the strain gauge rosettes, where it is mostly used in the dynamic applications. Okay, so this is about the application of the strain gauge rosette. Now we'll start with the numericals of the strain rosette. So in the part number 1 also we have discussed the importance of this particular table. So once again I will repeat, that is, in this particular table the different formulas are given for the different rosettes, as we have to calculate this particular all the unknown parameters. That is, I have to calculate the principal strength, that is epsilon 1, epsilon 2, then I have to calculate the maximum shear strain, then I have to calculate the principal strain direction, then I have to calculate the principal stresses, that is sigma 1, sigma 2, and at the end I have to calculate the maximum shear stress. But to calculate all these parameters, which parameters are required, that is, if I have to calculate the epsilon 1 and epsilon 2, initially I have to calculate the epsilon x, epsilon y, gamma xy. In all these particular formulas, these parameters are very important, but in the statement of the problems, this epsilon x value, epsilon y value, gamma xy, it is not given directly. Instead of that, the values of epsilon a, epsilon b, epsilon c, epsilon d, like that parameters are given in the statement of the problems, and from this particular epsilon a, epsilon b, epsilon c, initially I have to calculate these three values, that is epsilon x, epsilon y, and gamma xy, and these three values I have to put in this all the equations to find out the unknown parameters. Therefore this particular table is very important. So whatever the epsilon x, epsilon y, and gamma xy value is there, this all the three values are different for the different types of the rosettes. So this column represents for the 3 element rectangular rosettes, this is for the 4 element rectangular rosette, this is for the delta or equiangular rosette, and this is for the T delta rosette. So initially in the statement of the problem, the type of rosette is also mentioned, so we have to identify that on which rosette the problem is asked, and from that particular name we have to identify the type of rosette, and according to that given data, initially I will calculate the value of epsilon x, epsilon y, gamma xy, and these three values I will put in this particular all the 5 equations to find out the unknown parameters. Therefore this particular table, which is very important for the conversion purpose, and these are the 5 important formulas which we have to calculate in all the types of rosettes. So now we'll start with the numericals, that is numericals on the rosettes or the strain gauge rosettes. Now I will start with the first numerical of the strain gauge rosette. So once I will read the statement first, and from that statement initially we'll understood which given data they have mentioned, and whatever the problem they have given, for which type of rosette the problem is asked. So now I will read the statement first, that is, a typical rectangular rosette gives the following readings. So whatever the type of rosette they have mentioned the rectangular rosette, but there are mainly two types of the rectangular rosette, that is 3 element and the 4 element. But here they have not mentioned the word that is 3 element and the 4 element, but from the given data itself we can understood that whatever the statement they have mentioned, whether it is mentioned for the 3 element and the 4 elements. So from this particular first statement I can understand that the statement is given for the rectangular rosettes, then they have given the readings, that is epsilon a is equal to 430 microstrain, it is given in the microstrain. Then epsilon b represents the minus 230 microstrain. Epsilon c is given 550 microstrain. Then calculate first parameter, principal strain, that is I have to calculate the epsilon 1, epsilon 2. Principal stresses, that is I have to calculate the sigma 1 and sigma 2, and their orientation, that means direction of principal strain and the principal stresses I have to calculate, that is I have to calculate the phi 1 and phi 2. And to calculate all these parameters, the two constants are required in the formula, that is E Young's modulus is equal to 2 into 10 raised to 5 Newton per mm square, and mu is equal to 0.28. So these are the all given parameters which is mentioned in the statement of the problem, but they have mentioned a rectangular rosette. But which type of rectangular rosette, whether 3 element or the 4 element? So from the given data itself we have to understand that whether it is for the 3 element or the 4 element. So if you go through the given data of epsilon a, epsilon b, epsilon c, so here only three strain gauges are there, because the epsilon a is applicable for the strain gauge number 1, epsilon b is applicable for the strain gauge number 2, and epsilon c is applicable for the strain gauge number 3. That means only three given parameters are there. Therefore directly I can say that from this particular given data, whatever the rectangular rosettes they have used, that rectangular rosette will be considered as a 3 element rectangular rosette. But here if they have given the additional strain, that is epsilon d, so due to that epsilon d the number of strain gauges becomes 4. Therefore I can say that whatever the strain gauge they have given, that is the 4 element rectangular strain rosette. But here only epsilon a, epsilon b and epsilon c is given, therefore only 3 strain gauges are there. And be specific, they have mentioned rectangular rosette, because sometimes that in the delta rosette also the 3 strain gauges are there, but delta rosette is only called as a delta or equiangular. But here in this particular statement they have mentioned a rectangular rosette, therefore we have to identify that whether it is 3 element or the 4 element. But according to the given data, it has been finalized that whatever the rectangular rosette is given, this is the 3 element rosette. That means epsilon a, epsilon b and epsilon c is given. Then the value of Young's modulus mu is given. So initially I have to write down all the given data, that is value of epsilon a is given, epsilon b is given, epsilon c is given. Then these two constant parameters are given, that is mu is equal to 0.28 and E is equal to 2 into 10 raised to 5 Newton per mm square. So if we have to go for the unknown parameters, so to calculate the unknown parameter, that is first one is a principal strain. So there are basically two types of principal strain, that is epsilon 1 and epsilon 2. So if I have to calculate the epsilon 1 and epsilon 2, so what I have to do, I have to write down the basic formula for the epsilon 1. So if I will read the formula for the epsilon 1 and epsilon 2 calculation, that is 1 half in bracket sigma x plus sigma y plus minus 1 half square root of sigma x minus sigma y bracket square plus tau xy square. So if I have to calculate the value of epsilon 1 and epsilon 2, initially I have to know the epsilon x, epsilon y and gamma xy, but it is not given in the statement of the problems. But whatever the table I have mentioned, from that particular table and from the type of rosette, by using the value of epsilon a, epsilon b and epsilon c, initially I have to calculate the value of epsilon x, epsilon y and gamma xy, and then only I can find out the unknown parameters. Therefore according to the given data and according to the types of rosettes, initially I have to calculate the epsilon x, epsilon y and gamma xy. Therefore from that particular table, that is for 3 element rectangular rosette, I have to calculate this particular values. So I will take that particular equations from that particular table, that is epsilon x is equal to epsilon a, which is mentioned in that particular table. Therefore epsilon x is equal to epsilon a is equal to 430 microstrain. Similarly from the table, epsilon y is equal to epsilon c. So again epsilon c is given, that is 550 microstrain. To calculate the gamma xy, so from the table the formula is available for the 3 element rectangular rosette, that is gamma xy is equal to 2 into epsilon b minus in bracket epsilon a plus epsilon c. So epsilon b, epsilon a, epsilon c is given, so I have to put all these three values in this particular gamma xy equation, and then I can calculate the gamma xy. So we have calculated the values of epsilon x, epsilon y and gamma xy from this particular all the given parameters and from the type of Rosettes. Once all these three parameters are calculated, then we have to go for our unknown parameters, that is first parameter, principal strains. So the formula is in front of you. I have to calculate the two principal stresses, that is epsilon 1 and epsilon 2. The formula is given in the form of positive and the negative, that is whatever this particular central portion is there, here one plus is there, one minus is there. As already I have told, if I have to calculate the epsilon 1, I have to take the addition of this equation and this equation. If I have to calculate the epsilon 2, I have to take the subtraction of this equation and this equation. So for the next step, so 1/2 is as it is. The epsilon x we have calculated from the top. We have to put the values of epsilon x. We have to put the value of epsilon y is equal to epsilon c as it is, plus minus this sign is also as it is, then 1/2 and square root of once again epsilon x minus epsilon y bracket square, that is 430 minus 550 bracket square, plus gamma xy also we have calculated, it is a negative value, therefore we have to take that negative value as it is, that is 1440 square, and from this particular equation I can calculate the value of epsilon 1 and epsilon 2. So initially I will take the addition of this particular terms and this particular terms. So I will take the, or I will calculate the epsilon 1 by making the addition, and by using the same equation, if I will take the subtraction, then I can calculate the epsilon 2. That means epsilon 1 is calculated by taking the addition or by doing the addition, and epsilon 2 is calculated by doing the subtraction. So one value is obtained a positive, that is 1212.49 microstrain, because all the values are in microstrain, and second value it is in negative, that is minus 232.49 microstrain. So these two parameters are called as a principal strains. Now what the next parameter they have asked, that is principal stresses. So we are having the formula for the sigma 1 and sigma 2 calculation also. What is the first formula? That is sigma 1 is equal to E upon 1 minus mu square into epsilon 1 plus mu into epsilon 2 into multiply by 10 raised to minus 6. So why this particular multiplication is required? That is, I have to calculate the value of sigma 1 in Newton per mm square. Therefore, for the conversion purpose, we have to multiply by 10 raised to 6. So due to that multiplication, you will get the sigma 1 directly in the form of Newton per mm square. So to calculate the sigma 1 equation, put the value of E, which is given 2 into 10 raised to 5, then 1 minus mu square, that is 1 minus 0.28 square, multiply by, in bracket, value of epsilon 1 already we have calculated, so take that value as it is in this equation, so this plus sign as it is, then we have to multiply by that is mu 0.28, then epsilon 2 already we have calculated value of epsilon 2, that is minus value, we have to take that minus value as it is in this particular equation, and finally we have to multiply by 10 raised to minus 6. Therefore you will get the answer directly in the Newton per mm square, that is the first principal stress sigma 1 is equal to 249.00 Newton per mm square. So this value represents the magnitude of first principal stress. Similarly, I have to calculate the magnitude of second principal stress, but the formula is somewhat different. That is the formula for the sigma 2 calculation, which is given in the list of the formulas, that is E upon 1 minus mu square into epsilon 2 plus mu into epsilon 1. In the sigma 1 equation, first parameter is the epsilon 1 plus mu into epsilon 2, but in the sigma 2 calculation, the first parameter is epsilon 2 plus mu into epsilon 1. So this is the basic difference, that is E upon 1 minus mu square, E upon 1 minus mu square is common for the sigma 1 and sigma 2 calculation, but only change for this particular parameter and from this particular parameter. So for the sigma 1 initially they have considered as epsilon 1, and for sigma 2 initially they have considered as a epsilon 2. So once again I have to put the values of all unknown parameters, that is E as it is, then 1 minus mu square as it is, then epsilon 2 already I have calculated, this epsilon 2 value we have to put here as it is, as with minus sign, then this plus sign as it is, then multiply by mu 0.28. Epsilon 1 also we have calculated, so we have to take that epsilon 1 as it is, and at the end don't forget to multiply by 10 raised to minus 6. From this calculation I will get the value of sigma 2, that is 23.22 Newton per mm square. So this is about the calculation for the magnitude of the principal stresses, that is sigma 1 and sigma 2. Then I have to calculate the orientation. That means I have to calculate the orientation of the direction of principal strains and the principal stresses, because whatever the strain is induced in that particular direction, in the same direction some amount of stress is also induced. Therefore we have to calculate the orientation with respect to epsilon a, because always we have to calculate such types of orientation with the horizontal strain gauge, and in the horizontal direction your epsilon a is there, or that epsilon a strain gauge is there. Therefore to calculate that orientation we are having the first formula, that is phi 1, which we have taken from that particular list, that is phi 1 is equal to 1 half into tan inverse of gamma xy divided by epsilon x minus epsilon y. So to calculate that particular phi 1, write down this 1 half into tan inverse as it is. So gamma xy we have calculated from the epsilon a, epsilon b, epsilon c. So this gamma xy I have to put as it is with their sign, that is minus 1440 divided by epsilon x, epsilon y also we have calculated from that particular table. So we have to put the value of epsilon x 430, epsilon y 550, and by making this particular calculation I can calculate phi 1 is equal to 42.61 degree. So this phi 1 represents the orientation of first principal strain or orientation of first principal stress with respect to epsilon a. Means from epsilon a, whatever the first principal strain is located, its angle is 42.61 degree. Now to calculate the value of phi 2, that phi 2 represents the orientation of second principal strain or orientation of second principal stress. So for that calculation simple formula is there. So whatever the phi 1 we have calculated, in that phi 1 only I have to add the 90 degree, and then I can calculate the further calculation. Therefore phi 2 is equal to phi 1 plus 90 degree. So put the value of phi 1, that is 42.61 degree from as it is, from this particular formula we have calculated, plus 90 degree we have to add, and you will get the second value, that is the 132.61 degree. And this particular angle or this particular inclination represents the position of second principal strain or the position of second principal strains from this epsilon a. So phi 1 represents the direction of first principal strain, and phi 2 represents the direction of second principal strain. So like that we have to calculate all these unknown parameters. So like that we have to solve the numericals based on the strain gauge Rosette. So whatever we have discussed, that is initially we have to identify that type of Rosette which is mentioned in the statement. Then from the given data also we can identify that for which Rosette the statement is given. Then by using all these given parameters we have to calculate the value of epsilon x, epsilon y, gamma xy. So all these values we have to calculate in all the types of Rosette by taking the reference of that particular table, and by putting all these three values in the number of unknown parameters we can calculate the principal strains, principal stresses and their directions. So like that we can solve the problems based on the strain gauge Rosette. Now we'll discuss about the second problem, that is I will read the statement first. So whatever the statement they have given, that is the strain gauge readings are measured by the T delta Rosette. So be specific, they have mentioned the statement is given for the T delta Rosette at a point in stressed body are given by. So if that particular body is subjected to the loading, so some amount of strains gauge readings are recorded by using that particular Rosette, and it is represented in the form of epsilon a is equal to 225 microstrain. If it is not, if this particular unit is not mentioned, so automatically you have to consider it as a microstrain. Then epsilon b 300 and 5, then epsilon c minus 294, and epsilon d is equal to minus 65 microstrain. So there are four readings are given from epsilon a to epsilon d. Why four readings? Because in the T delta rosette there are four strain gauges, and in delta rosette only three strain gauges are there. But here they have already mentioned the type of rosette is the T delta rosette, as well as from this particular given parameters also I can say that there are four strain gauge readings are there, which is applicable for the T delta rosette. Therefore, in the statement it is very important to identify the type of rosette, because based on this particular type of rosette I have to go for the further calculation. Then what they have asked, determine the principal strains, that is epsilon 1 epsilon 2, then principal stresses sigma 1 sigma 2, maximum shear strain, that is gamma xy or gamma max we have to calculate, then principal strain directions, that is phi 1 and phi 2 we have to calculate, and maximum shear stress, that is tau max also we have to calculate. And they have mentioned some constant parameter, that is E is equal to 200, it is given in gigapascal, 200 gigapascal, and mu is equal to 0.3. Now as we have to calculate all these unknown parameters, but initially we have to calculate the values of epsilon x, epsilon y, and gamma xy, which is not given in the statement of problem. But to calculate the value of epsilon x, epsilon y, and gamma xy, this epsilon a, epsilon b, epsilon c, and epsilon d are useful as per as per taking the reference of that particular table. So we'll solve the numericals. So that is for the T delta rosette. From that particular table I can calculate the value of epsilon x is equal to epsilon a by taking the reference of that table, that is 225 microstrain. So epsilon y is equal to epsilon d, because it is mentioned in that particular table. Once again it is equal to minus 65 microstrain. Then gamma xy is equal to 2 upon root 3 into epsilon b minus epsilon c. So this particular formula I have taken from that particular table. This gamma xy is given for the T delta rosette. So from that table I have written the equation 2 upon root 3 as it is, multiply by epsilon b I can put, that is 305 minus epsilon c. Here it is given negative, therefore we have to take that negative value as it is, and I can calculate the gamma xy, which is equal to 691.66. That means by taking the values of epsilon a, b, c, and d, I have calculated epsilon x, epsilon y, and the gamma xy. Same procedure we have to follow for all the types of rosettes, that is by identifying the name of rosette. Initially I have to calculate the all these three parameters, then one by one we'll calculate the unknown parameters. That is, first one is a principal strain. Again the same formula, epsilon 1 I have to calculate, epsilon 2 I have to calculate. The formula is given in the form of positive and negative. So to calculate epsilon 1, take the addition of this particular two equation. If I have to calculate the epsilon 2, take the subtraction of this particular equation. By taking the addition first, I have calculated epsilon 1 by putting all the values. That means whatever the epsilon x, epsilon y, and gamma xy we have calculated, put all these values in this particular equation. That is epsilon x we have kept, epsilon y we have kept. Similarly here also we have put the values of epsilon x, epsilon y, gamma xy, and by making the addition first I have calculated epsilon 1, and it is of 454.97 microstrain, and by taking the subtraction I have calculated the epsilon 2, which is equal to minus 294.97 microstrain. So this is the magnitudes of the principal strains. Then calculate the principal stresses, that is sigma 1 and sigma 2. So for the sigma 1, again the same formula from that particular list of the formulas, that is E upon 1 minus mu square into epsilon 1 plus mu into epsilon 2 into 10 raised to minus 6. So put the values of E, mu, then epsilon 1 which we have calculated initially, that epsilon 1 we have to put as it is, then that mu is given, then epsilon 2 it is in negative, so we have to take that value negative as it is, multiply by 10 raised to 6. So from this particular calculation I can calculate the first principal stress, that is sigma 1 is equal to 80.54 Newton per mm square. Similarly by using the equation that is for the sigma 2 by putting all the values. That is, initially I will put the values of epsilon 2 which we have calculated, that is negative sign, plus uh, that mu once again epsilon 1 as it is multiply by 10 raised to 6, and by solving this particular equation I will get the second principal stress, that is minus 34.83 Newton per mm square. So this is about the calculation of principal stresses. Then maximum shear strain. So to calculate the maximum shear strain, the formula is available with us, that is gamma xy is equal to square root of epsilon x minus epsilon y bracket square plus gamma xy bracket square. So from this particular equation I can calculate the maximum shear strain, that is gamma xy is equal to, put the values of epsilon x, epsilon y, take the square of that, then gamma xy already we have calculated, and by making this particular calculation I can calculate the maximum shear strain, which is equal to 749.99 microstrain. So this is the formula to calculate the maximum shear strain. Then the fourth parameter is direction of principal strains, means I have to calculate the phi 1 and phi 2. So to calculate the phi 1, the formula is available, 1 half tan inverse of gamma xy divided by epsilon x minus epsilon y. So we have to put the value of gamma xy which we have calculated here. This is gamma xy. Then we have to put the value of epsilon x, epsilon y. From this particular calculation I can calculate the first direction, that is 32.62. So this represents the phi 1 value, and to calculate the phi 2, the formula is available, phi 2 is equal to phi 1 plus 90 degree. So in this 33.62 I have to add the 90 degree, and this 123.62 degree represents the direction of second principal strain. And the last parameter, that is the maximum shear stress. So formula for the maximum shear stress calculation is tau max is equal to sigma 1 minus sigma 2 divided by 2. So make the subtractions of sigma 1 and sigma 2 by putting that values in this particular formula and divide by 2. You will get the value, that is tau max is equal to 57.68 Newton per mm square. As the sigma 1 and sigma 2 are available in Newton per mm square, therefore the tau max also you will get in the form of Newton per mm square. But whatever the strain values are there, that strain values are available in the form of micro strain, and the stresses values are available in the form of Newton per mm square, and directions are available in the form of degree. So like that, same parameters we have to calculate for all the three types of Rosette. But once again I am telling, that is in the statement, first of all we have to identify that for which Rosette the statement is given. It is mentioned, that is for example in this particular statement T delta Rosette is there, and from that particular T delta Rosette I can calculate the further calculation. That means this word or this type of Rosette is very important to calculate the values of epsilon x, epsilon y and gamma xy, and same process you have to follow in all the types of problems related to the strain Rosette. That means calculate these three values, epsilon x, epsilon y, gamma xy, and then by using all these three values I can calculate the unknown parameters, and same five parameters you have to calculate in all the three types of Rosette. Sometimes they are interested to find out all the five parameters, sometimes they are interested to find out only principal strain, principal stresses and their directions. Sometimes they are interested to find out only three parameters, sometimes four parameters, sometimes all the five parameters. But as all the formulas are available with us, so by using that all the formulas and by using all these particular unknown values I can calculate all these parameters from this particular given data. So this is about the second problem related to the strain gauge Rosette. So like that we have discussed about the two problems. That is one problem we have discussed on the rectangular Rosette, that is B specific, that is 3 element rectangular Rosette. So we have calculated all the unknown parameters from the required data. Then we have discussed about the second problem, which is for the T delta Rosette, and we have solved this particular problem to calculate the same unknown parameters. In the last problem whatever we have discussed, that is T delta Rosette, in that problem we have calculated all the five parameters as per their requirement. So like that we have discussed the two numericals based on the strain gauge rosettes or the strain rosette. Uh, Remaining numericals we'll discuss in the next lecture. That is based on the numericals based on the equiangular rosettes or the delta rosette. Then we'll discuss the numericals based on the four element rectangular rosettes. So from this particular numericals only we have to understood that for all the types of rosette the procedure is same. That is what is the procedure? Initially in the statement we have to identify that type of rosette. Then we have to identify that given data, and from that particular given data we have to find out the epsilon x value, epsilon y value, gamma xy value, and from this particular three values I have to calculate remaining all the unknown parameters. In most of the 90% problems they are giving the values of epsilon a, epsilon b, epsilon c, and sometimes epsilon d. Only 10% chances are there where they are giving the direct values of epsilon x, epsilon y, and gamma xy. If direct values are given, that is need not required to take the reference of that particular table. Directly by putting all these three values in the unknown parameters we can calculate the all the unknown parameters. But if the given data is mentioned in the form of epsilon a, epsilon b, epsilon c, then we have to take the reference of that particular table, and from that table we have to calculate the values of epsilon x, y, and gamma xy, and then we can find out the remaining unknown parameters. So in this particular chapter, that is in the part 2, we have discussed about the applications of the strain gauge rosette, that is basically where it is used. Then we have discussed all the important formulas, all the unknown parameters which we have to calculate, and we have discussed about the two numericals, that is how the numericals are solved for the strain rosette. So in the next part, in the part number 3, we will discuss some more numericals or more examples based on the strain gauge rosettes. Thank you.